Hello students, welcome to EPG Pathshala. I am Dr. Ayushi Paliwal from University of Delhi. So students, today we are going to discuss about the module Calculation of Density of States, that is DOS, from the paper Physics at Nanoscale. So students, let us see what we are going to learn in this module. First, we will calculate DOS for 3 dimensions bulk. Then we will calculate for 2 dimensions well. Then for 1 dimension wire. Next, we will also calculate the density of states for 0 dimensions, that is a quantum dot. We will also evaluate the density of states in the conduction band and in the valence band. The Fermi level positions for a 2-dimension well and a 1D wire will also be studied. So let us start with the basic introduction about the module. The density of states is the main characteristic of any quantum mechanical system. So in the physics of condensed matter, the DOS is usually obtained via an integration over the first Brillouin zone. The density of states function describes the number of states that are available in a system and is essentially for determining the carrier concentration and energy distributions of the carriers within a semiconductor. So single, double and triple integrals need to be solved if we work on 1D, 2D or 3D systems respectively. So the variables in any case are the components of the electron's wave vector in its movement through the periodic crystal. The integrands are the local density of states, that is LDOS. The DOS by definition depends only on the energy, while the LDOS depends also on the variable K. In the homogeneous ideal crystals, calculating the DOS requires the integration of singular functions in the reciprocal space of the vector K, which makes the numerical calculation much more difficult than the integration of continuous functions. So in this, we will find out certain methods that deals with singular integrals. In contemporary solid-state physics, great attention is given to the systems of low dimensionality due to their applications in nanotechnology. Quantum dots, quantum threads, and plane heterostructures, quantum wells, and superlattice possesses physical properties, whether they are microscopical and macroscopical, because of the fundamental physical parameter dimensionality, which will be 0D, 1D and 2D for quantum dots, threads and wells and superlattices. So the systems of reduced dimensionality preserve periodicity in 1 or 2 variables and they loses it in 2 or 1 respectively, in 3 in the case of quantum dots. So in the context of nanostructures, the computation of the DOS has its peculiarities. So, one of the main tasks in the theory of systems of low dimensionality is numerical and analytical in few cases where this can be done. So, calculations of the DOS for real materials. Density of states for three-dimensional systems, that is for bulk. So we consider a K-space as shown in this figure, which is filled with a uniform grid of points, each separated in the units of 2 pi by L along any axis. So the volume of K space occupied by each point is 2 pi to the power cube divided by Lx, Ly, Lz. So the number of modes in a sphere, first in R space, it is 4 pi r square dr by V, and in the K space it is 4 pi k square dk by Vk, which is equal to 4 pi Lx, Ly, Lz k square dk divided by 8 pi cube. So students, continuing our discussion on DOS in 3 dimensions, say the particle in an electron and we consider spin up and down, then we multiply n by 2. So that is n prime is equal to 2n equal to k cube by 3 pi square multiplied by Lx, Ly, Lz. So this is the total number of states in a sphere. Now consider the density, that is rho is equal to k cube by 3 pi square, which is obtained by dividing n prime divided by Lx, Ly, Lz. Now here k is equal to root of 2me by h cut square. So this is the number of states per unit volume. Now consider the energy, which is defined as rho prime is equal to d rho by dE, which is equal to d of k cube by 3 pi square, that is putting the value of rho, divided by dE, equal to 1 by 2 pi square multiplied by 2m by h cut square the whole power 3 by 2 multiplied by root e. So as you can see in this figure, for the 3-dimension case, the density of states is proportional to root e, and this is shown in this figure. Now students, let us discuss the density of states in 2 dimensions, that is for the well. Here we have 1D that is quantized. So let us assume it is the z direction. The total energy of this system is the sum of the energy along the quantized direction plus the energy along the other 2 free directions. It is expressed as Et is equal to h cut square kz square by 2m plus h cut square k square by 2m, which is equal to En plus Exy, where kz is equal to n pi by Lz and k square is equal to kx square plus ky square. Now consider an area in the K space which is given by A is equal to pi k square, where for the particle kx is equal to 2 pi by Lx and ky is equal to 2 pi by Ly. So, the area of a given mode is then kx, ky, with the total number of modes n in the area being n is equal to pi k square by 4 pi square multiplied by Lx, Ly. This is equal to k square Lx, Ly by 4 pi. Now again, if the particle is an electron and we consider the spin, then multiply by 2, we get n prime is equal to 2n equal to k square Lx, Ly by 2 pi. Continuing our discussion over density of states in 2 dimensions, consider now the density, that is rho is equal to n prime by Lx, Ly equal to k square by 2 pi, and we have k is equal to root of 2me by h cut square, and the energy density is defined as rho prime is equal to d rho by dE equal to m by pi h cut square. This is the energy density of the subband for a given kz or En. For each successive kz, there will be an additional m by pi h cut square and hence the another subband. Therefore, the density of the states is written as rho prime 2d is equal to m by pi h cut square summation over n theta e minus En, where theta is the Heaviside wave function. So now students, as you can see in this figure, this shows the density of states in 2D, and here it shows a step-like function, and the below state shows the occupied states. Now let us discuss the density of states for one-dimensional system, that is a wire. Consider now the situation where there are 2 dimensions confined and only 1 degree of freedom, say the x direction. So the total energy of the system can be written as Et equal to h cut square kz square by 2m plus h cut square kz square by 2m plus h cut square k square by 2m equal to En plus Em plus Ex, and k is equal to kx equal to 2 pi by Lx. Now furthermore, along the confined directions, kz is equal to n pi by Lz and ky is equal to m pi by Ly, where m and n are the integers. Now consider a length 2k, so the number of modes along this length is n is equal to 2k by kx equal to 2k by 2 pi by Lx equal to k Lx by pi. So now, in order to calculate the number of states along the line, we consider an electron again and ensure to take into account the spin degeneracy, and n prime is equal to 2n equal to 2k Lx by pi. Now let us consider the density of states in one dimension. That is, we are continuing a discussion. So here the density rho is equal to n prime by Lx equal to 2k by pi equal to 2 by pi multiplied by root of 2me by h cut square is the number of states per unit length. So the energy density is rho prime is equal to d rho by dE equal to 1 by pi multiplied by root of 2m by E h cut square. This is the energy density for a given n m value. The expression taking into account all the mn combinations. So here the rho prime for one dimension is equal to 1 by pi multiplied by root over 2m by h cut square summation over nm of 1 by root of e minus enm multiplied by theta e minus enm, where theta is the Heaviside function. So here, as you can see in this figure, this shows the density of states in one dimension, which shows a spike-like behavior. Let us now discuss the DOS for zero-dimensional systems, that is for a quantum dot. Here all the three dimensions are confined and the total energy ET is equal to h cut square kx square by 2m plus h cut square ky square by 2m plus h cut square kz square by 2m. That is, it is equal to Em plus En plus E naught. So for the integrals m, n and o, this kx is equal to m pi by lx, ky equal to m pi by ly and kz is equal to n pi by lz. So as you can see in this figure, the density of states are being shown with the varying energy for a quantum dot, that is for a zero dimension, and the density of states are represented by rho prime 0d equal to a delta function of E minus EMNO. So the density of state is a series of delta functions. So now students, if we are confining the electron motion in at least one spatial dimension, it affects the energy levels and the density of states. So as you can see, for the bulk, that is 2D, we have a continuous variation of density with the energy. Now for a quantum well, that is for 2D, it varies in a step-like fashion. For a quantum wire, that is for 1D, the density of states varies discontinuously, and for a quantum dot, it is like a delta function, that is for zero dimension. So students, let us discuss more about the density of states. Let us now evaluate the density of states in the conduction band. For this, we need to know the probability that an electron will occupy a given state of energy E. The probability PE is referred as the Fermi-Dirac distribution. In addition, we need to know the density of states rho prime. The density of states has units of number of unit volume per unit energy. Therefore, rho prime dE is the number of states per unit volume. So the number of occupied states at a given energy per unit volume is therefore Ne as a function of E is equal to PEE rho prime E dE, where the Fermi-Dirac distribution is Pe as a function of E is equal to 1 by 1 plus exponential E minus EF by kT. Now here EF is the Fermi energy. The total concentration of electrons in the conduction band is therefore the integral over all available energies, that is Nt is equal to Ec to infinity PEE multiplied by rho prime E dE, where Ec is the energy where conduction band starts. Now for the case of three-dimensional material, this rho prime is equal to 1 by 2 pi square multiplied by 2me by h cut square to the power 3 by 2 multiplied by root e. So now taking into account the conduction band begins, then the rho prime will become, now here we will replace E by E minus Ec. Now putting the value of rho prime, then the total concentration of electrons in the conduction band is given by Nt is equal to 1 by 2 pi square multiplied by 2me by h cut square to the power 3 by 2 integral over Ec to infinity 1 by 1 plus exponential E minus EF by kT multiplied by root of E minus Ec dE. This integral is called as the Fermi integral or Fermi-Dirac integral. And now putting the assumption as E minus EF is very much greater than kT and solving the integral using the limits of integration and making use of the gamma function, then Nc is equal to Nt is equal to 1 by 2 pi square multiplied by 2me kT by h cut square to the power 3 by 2 multiplied by exponential minus Ec minus Ef by kT multiplied by gamma 3 by 2. Now if we'll assume capital Nc to be equal to 1 by 2 pi square multiplied by 2me kT by h cut square to the power 3 by 2 multiplied by gamma of 3 by 2. Now Nc equal to Nt will be equal to capital Nc multiplied by exponential minus Ec minus Ef by kT. So this is the expression for the effective density of states of the conduction band. Now let us calculate the density of states in the valence band. The number of holes at a given energy per unit volume is given as NH as a function of E is equal to PHE multiplied by rho prime E dE, where we use the relation PEE plus PHE, that is the total probability equal to 1. So the probability for the holes will be equal to 1 minus 1 by 1 plus exponential E minus EF by kT. And the density of states is rho prime equal to 1 by 2 pi square multiplied by 2 mh divided by h cut square to the power 3 by 2 root of EV minus E, where EV is the energy where valence bands starts. So the total concentration of holes in the valence band is the integral over all the energies. So PT will be equal to integral from minus infinity to EV over PHE multiplied by rho prime E multiplied by dE. Now putting the value of pH as a function of E and rho prime as a function of E and integrating that the limits of integration by changing them and making use of the gamma function, then PT is equal to 1 by 2 pi square multiplied by 2 mh kt by h cut square to the power 3 by 2 multiplied by exponential minus EF minus E by kt multiplied by gamma of 3 by 2. So PT is equal to NV exponential minus EF minus E by kt. So this is the expression for the effective density of states in the valence band. So let us summarize what we have learned in this module. Firstly we discussed the two-dimensional electron gas. Secondly, the basic properties of low-dimensional systems. Thirdly, we calculated the density of states for 3D, 2D, that is for a well, and 1D for a wire. Next, we also calculated the density of states for zero-dimensional system, that is for a quantum dot. Lastly, the expression for DOS in the valence band and the conduction band, they were obtained. Thank you.